Okay, good afternoon, everybody. I think we'll go ahead and get started. It's 12 o'clock. So the last two lectures were online. I wasn't feeling well last week, so, with all the protocols, I stayed home. I managed to get the lectures up. I didn't manage to do a whole lot else, so if you're still waiting on an email from me, I'll get back to you as soon as I can. It also got me behind in test marking, so I was a little behind. The TA was away, she got behind. We're doing our best to have the test ready for Wednesday. If not Wednesday, then it would be Friday. You'll know when the test is marked because I'll post your grade on Brightspace. My intent is to get the grades posted and then come to your lab sections to pass them back. If you see the grade up and you don't want to wait for your lab section, feel free to drop into my office and get your test back there. I'll also post the test solutions if I haven't done that yet. I can't remember if I posted them or not. Okay, so we did a lot of stuff in those two online lectures. I'm going to carry forward assuming you've watched them. If you haven't watched them, then just try and keep up as best you can. But in the meantime, are there any questions before we get started? No? Okay, so last time I said in the first bit that I wanted to pass out wintergreen lifesavers so you could do the experiment. So if you don't have them at home, I did bring a bag, you can come take one. And then I brought a bag of candy because it's Halloween, so you can kind of get some candy at the end if you want. I thought maybe it was a little bit dumb to bring candy, but my kids assured me it was okay, that everybody likes candy. So I will be running at the end of class, but I'll leave these here for you to get some as you scoot out. So one of the main things we did at the end of Friday's lecture was the relationship between potential and electric field. And then I'm going to come back to this slide that I think was also Friday's lecture. Maybe it was Wednesday's. We know the relationship between force and potential energy. Force is the derivative of potential energy, or potential energy is the integral of force. So that's how you go back and forth between those two. Between force and field, force is Q times E, or E is F over Q. Between energy and potential, energy is charge times potential, or potential is energy divided by charge. And we said we were going to get the relationship between potential and field, and that was the last bit of the last class. So I'm just going to fill in those relationships here on this slide. So delta V is equal to minus the integral of E dot ds, that's the general form. Or for constant electric fields, delta V is minus E dot delta S. So that's potential from field. To get field from potential, you work backwards. So your component of electric field is minus the change in potential with regards to that direction, or it's the derivative with regards to that direction. Really, that should be right here. That negative sign is really important. That tells us that electric field always points towards lower potential. So that negative sign is really important. There's a couple of questions on the assignment to find the electric field if you know the potential. Mostly people get that question wrong because they drop the negative sign. So just watch out for that as you're doing the assignment. And then last, we'll just remember that S is the path that you take. So there's our summary from last day. We'll get into an example to start off today. Honest to goodness, I'm still a little fuzzy brained from not feeling well, so if something doesn't make sense, chances are good it's me, not you, so please do ask questions. So for our first example, we're going to ask what's the electric potential between the plates of a capacitor. We do lots of work on capacitors. We've already talked about the field between capacitor plates, and we talked about the energy, so now let's talk about the potential. So first of all, let's make sure we understand the details of the electric field and the geometry. Our electric field goes from a positive plate to a negative plate. In this picture, if we take our positive x-axis to the right and our positive y-axis to be up, then our electric field points to the left. and our electric field vector would be negative the magnitude in the x direction. That's a typical way to write a vector. Or the x component of the field would be negative the magnitude of the field. Yeah, points left, so it's negative. Our x-axis, we'll take x equals 0 at the negative plate. Because that's our standard, we set the negative plate to be our reference point or our ground. So at the plate is where our parameter is equal to 0. And generally we say that the distance between the two plates is d. So over here at the positive plate, that's x equal to d. We want to ask about the potential between the plates. So let's start with the fact that our change in electric potential as you move along some path is negative the electric field dotted with the path. So we've already kind of established the electric field. Let's make sure we understand what the path is. So for our path, let's start at one point and move to the right. So there's our path, delta S. We see that our path is going in the x direction. So that's going to be positive delta x by half. Okay, so I'm choosing my path to be parallel to the x direction here. We will do an example where it's not parallel, and we'll see what difference that makes. So for our scalar product, two ways you can do it. You can do E times the magnitude of delta S times the angle theta, or you can do it with components. I'm going to write it out in component form. So EX times delta X plus EY times delta Y plus EZ times delta Z. The reason I like writing it out this way is we see that our electric field only has an x component. So even if our path did have delta y and delta x parts, even if it did go up or out, it wouldn't make any difference to the potential because these two components of electric field are 0. So if we moved in y or z, it wouldn't do anything at all to the potential. It's kind of why I like this form because it shows that that's true. So EY is 0, this whole bit is 0. This whole bit is 0. So now we've got minus, our EX is negative because it points left, the magnitude of the electric field times our delta X. Here we remember that delta V would be V final, subtract V initial. That minus times a minus is a plus. The delta X would be X final minus X initial. Any good here? Basically, we just wrote down the equation. So let's think about what do we mean by x final and x initial. X initial, we called 0 if we start at the negative plate. That tells us that V initial is going to be 0. And x final, if that's equal to D, then our V final would be equal to E times D. So overall, the total potential difference between two capacitor plates would be the potential, it would be the electric field times the plate separation. And then the last thing we would probably put in is that our electric field points from high potential to low potential. So our positive plate would be high potential. Our negative plate would be low potential. So here this kind of makes sense. 0 is lower than the positive number, so that's our lower potential plate. Okay, good. Okay, we could, if we wish, draw a graph of this electric potential. So I had put S on my preloaded slides. I'm going to change that to X. So if we're at the plate where x equals 0, our potential is equal to 0. As we get over to the positive plate, it kind of increases linearly. And then delta V. Then we ask here in this one, what is the motion of a positive or a negative charge released from rest? This one is kind of a recap of what we did before. So how do charges move in an electric field or in a region with potential difference? If we let a positive charge go in between those plates, so if we just have a positive here and release it from rest, a positive charge would feel a force that's parallel to the electric field, so it would move in the same direction or with the electric field. So it would move from here towards the negative plate. That would be towards an area with lower potential energy, because our potential energy is the charge times the electric field times the position relative to the negative plate, and also towards lower potential. We can also ask what happens to the negative charge. So this one is kind of interesting. If we have a negative charge and release it from rest, the electric force is going to point to the right because force is charge times electric field. And the charge is negative, so the force and the field are opposites. So it moves against the electric field. Moves against the electric field. The potential energy here is still 0 because it's Q times E times the position. The potential over here, potential energy, is Q times E times the position. Where your charge is negative, it would be a negative potential energy over here. So it still moves towards lower potential energy. Okay, so this is true of everything. Things released from rest will move towards lower potential energy. But our negative charge moves towards high potential. Okay, so higher potential gives it lower potential energy. Any questions? So that looks after more or less the behavior. Let's do an example with some numbers. So a capacitor has 2 centimeter square plates, which contain equal and opposite charges of 3.75 microcoulombs. They're separated by 0.1 millimeters. So 0.1 millimeters is our plate separation. You can label this up here if you wish. So part A, find the charge density of the plates. So here we just have to remember, what do we mean by charge density? That would be charge divided by area. It'd be surface area charge density. So A, sigma equals charge divided by area. 3.75 times 10 to the minus 6 coulombs. This symbol of microcoulombs, this would be a symbol you're expected to remember on a test. If you ask me micro during the test, there's about a 50-50 shot that I won't tell you. So you should remember micro and nano for sure. The area of a square would be length times length, or length squared. So 0.02 meters squared. Gives us a charge density of 9.375 times 10 to the minus 6 coulombs over meters squared. So part A is really straightforward. Part B, find the electric field between the plates. Here's where we have to remember, how do we find the electric field if we know about the charge density? So this is something we did in a previous class. The electric field is equal to sigma divided by epsilon naught. 9.375 times 10 to the minus 6 coulombs per meter squared, divided by 8.85 times 10 to the minus 12 coulombs squared over newtons meters squared, to give us an electric field equals minus 1.06 times 10 to the 6 newtons per coulomb. My direction I got here just from the picture. So I calculated the magnitude by sigma over epsilon naught, and I looked at the picture to see that it points left. That's where my negative I hat comes from. So I'll put in my coordinate system as well. Here you might also say from positive towards negative. That would be okay as well, because that's the general direction of an electric field. So far, so good? A proton moves along the path shown. So here we have a path where we're moving in both x and y. So we've got a proton, that means we know the charge, with constant speed. So this means that the acceleration will be 0, so constant speed. Part C, find the change in potential difference as the proton moves along this path. So our proton starts here and it stops here. So we're finding the potential difference, that's delta V, change in potential difference. Delta V is minus E. It's E dotted with the path. Sometimes I call the path delta S. Here in this picture we called it delta R. That kind of change in notation, it's a little bit on purpose just to make sure you recognize what we're dotting E with. So it's E dotted with the path. So you have to identify what the path is. E dot delta R. So our path has two bits. It has a horizontal bit and it has a vertical bit. The horizontal bit we would call delta x, the vertical bit we call delta y. So in our scalar product, we would do negative ex times delta x plus ey times delta y. And remembering that the whole thing has to be negative. So we can put in our numbers here. Our electric field is negative of our x component of electric field. So if we look at our vector for electric field, Ex is minus 1.06 times 10 to the 6, and Ey is equal to 0. So we can put our components in here. Our delta x, it goes all the way across between the two plates. So our delta x is 0.1 times 10 to the minus 3 meters. Plus Ey is 0 times delta y, which we don't actually know. Right? But it doesn't matter because Ey is 0 anyway. Put all that through the calculator and we should get positive 106 volts. If we stop and think about our answer a moment, make sure we're happy with the sign. The proton has moved from the negative plate towards the positive plate. We know electric field points from high potential. So we see that our proton ultimately moved from a low potential to a high potential. So the potential increased, so we're happy with the sign of the change in potential there. Still good? Okay, part D. Find the change in electric potential energy as the proton moves along this path. So for this part, we know our delta V. We know it's a proton, so we know the charge. We're asked for the change in potential energy. So this is leading us to use the relationship between energy and potential to find the change in potential energy. So delta U, change in electric potential energy, is Q of the proton times delta V. Charge of a proton is 1.6 times 10 to the minus 19 coulombs. Positive charge because it's a proton. If it were an electron, it would be the negative charge. Times our 106 volts gives us 1.69 times 10 to the minus 17 joules. Our potential difference was positive. Our change in potential difference was positive. So our change in potential energy is positive. Okay, any questions about this bit? Okay, last bit. Find the work done by the electric field as the proton moves along this path. So the work done by the internal forces, so the work done by the electric force, or the force due to the electric field, is negative of the change in electric potential energy. So it's negative 1.69 times 10 to the minus 17 joules. At this point, the question doesn't ask it, but you might stop and think about the sign of that work done and what did that mean. So the work done has a negative sign. It means that the electric force did negative work. If you remember that work is the scalar product between force and displacement. If your work is negative, then the force and the displacement are in opposite directions. And that's exactly what's happening here. Our proton is positive charge. The electric force is to the left. So the force is to the left, but the displacement is to the right. So the force is one way, the displacement is the other way. That's opposite directions. That means it's negative work. It means our proton is going against the force. Why would something ever go against the force? Well, it must have been pushed. Okay, so the only way to get this proton to move from here to here is something had to go in and push it. That's what it means that the work done by the electric field is negative, so it had to be pushed into place. A part F to this problem could be find the work done by external forces to move the proton. That work done would just then be the positive of this because the net work has to be zero because it's constant velocity. So that could be a part F to this problem. Okay, questions? This one is kind of a standard question. So for the next example, there's one like this on your assignment, so this might help people out who are struggling with this next question. In a certain region of space, the electric potential is given by this expression. I was completely lazy here. I didn't put in any units on my 5, my -2, or my 1. Of course it has units. Overall the potential has to be in volts, but I just didn't want to write it in. So technically this unit right here on the 5 would be volts per meters cubed. On the -2 would be volts per meter. And on this 1 would be volts per meter squared. Okay, so it does have units. I just didn't write them in because it looks kind of gross. So part A, find the electric potential where x is 1, y is 1, and z is 1. That one is just a plug and chug. You put in x, y, and z all equal to 1. So V of 1, 1, 1 is equal to 5 times 1 cubed minus 2 times 1 plus 1 squared. And that gives us an answer of 4 volts. You just put in your values for x, y, and z. The next bit is where most of the work comes in. Find an expression, so that means find an equation for the electric field. Here's where we have to remember the relationship between field and potential. And that relationship is that the x component of electric field is negative the derivative of potential with respect to x. Okay, so how the potential changes in the x direction gives us the x part of the electric field. We've seen this symbol before, this dye symbol. That's our partial derivative. So we're taking the derivative of this equation. We're treating x as a variable and everything else is constant. So we're doing negative the derivative of 5x cubed minus 2y plus z squared. So that's going to be minus, so dropping that negative sign, make sure you don't do that. The derivative of 5x cubed, these are the derivatives I more or less expect that you can do in your head. So I figured you did loads of those in math, 1,000. So 3 times 5 gives us 15. Then x cubed goes to x squared. The derivative of minus 2y, we're treating y as constant, so that bit of the derivative is 0. Z squared is constant, so that's 0. And overall, we're left with minus 15 times x squared. So there's our x component of the electric field. Next, we'll do y and z. So EY equals minus the derivative of potential with respect to y. So the derivative of 5x cubed would be 0. The derivative of negative 2y would be negative 2. And the derivative of z squared would be 0. Overall, we're left with plus 2. And then likewise for our Z component. So the derivative of 5x cubed with respect to z is just 0. We're treating x as constant. The derivative of negative 2y is 0 because we take y as constant. And the derivative of z squared would be just 2z. That gives us the components of the electric field. To properly finish this question, you would have to write the electric field as a vector. So the electric field would be minus 15x squared. That's the x part, so it gets the I hat. Plus 2, that's the y part, so it gets the j hat. And minus 2z, that's the z part, so it gets the k hat. So there's our electric field. And part C says find the electric field at x, y, and z equals 1. So we just put in x, y, and z equals 1. Okay, any questions? So that takes us through the relationship between field and potential. When we were doing the electric field stuff, we looked at the electric field around a conductor. Now we're going to look at the electric potential around a conductor. So let's ask, what's the electric potential on the surface of a conductor? We're staying with our conditions of we're in electrostatic equilibrium. So what's the potential on the surface and what's the potential inside the conductor? And then I suppose we'll add in that we're talking about a charged conductor. If nothing has any charge, then this is not really very interesting. So a couple of things that we should remember as we start this problem. If we have a charged conductor in electrostatic equilibrium, the electric field is equal to 0 inside the conductor. So when we went through those 4 properties of a conductor, this was one of those 4 properties. The third property was that the electric field was sigma over epsilon naught, and it was perpendicular to the surface. And that was just outside. So there's a couple of reminders of things we already know about conductors and electrostatic equilibrium. Let's have a look at the potential inside the conductor first, and then we'll do on the surface. So inside, we know that the change in electric potential is negative the integral of E dot ds. ds is a small element of our path, so let's make sure we know what we're talking about by our path. So we go from some initial point to some final point, initial to final. This is our path. And ds would be a little bit of that path. So in terms of our integral, that's what ds is. This integral is really easy to solve. It's negative of 0 dotted with ds. Because we're talking about inside the conductor, and we know inside the electric field is equal to 0. This tells us, super careful right here, this equation gives us the change in potential. That part's really important. It says that the change in potential is 0. If the change is 0, it means your potential V is constant. And if it's constant, that doesn't mean it has to be 0. Maybe it's 0, but it doesn't have to be 0. It could be 10,000 volts, right? The only thing that we really know is that it doesn't change. So we'll say that it does not have to be 0. So our electric field tells us about the change in potential. Okay? And if your field is 0, it means your potential is constant. It doesn't mean the potential has to be 0. So that deals with inside. Next, let's do outside. Or on the surface, sorry. So we've got inside done, on surface next. We're going to use our same equation. Delta V is the integral of E dot ds. Let's think about those two vectors. We're taking the scalar product of E and ds. Let's deal with ds first. So we're taking a path along the surface of our conductor. I'll trace it as best I can. So from some initial point to some final point. This is our path. And a little bit of the path would be ds. So you see that we draw the path on the surface. That means the path is parallel to the surface because it's on the surface. So S is parallel to the surface because it's on the surface. Our electric field is perpendicular to the surface. So that means that our change in electric potential is negative E dot ds, which is negative E times ds times cosine of 90 degrees. E and ds are perpendicular because ds is along the surface and E is perpendicular to that. That tells us that delta V is equal to 0 and V equals constant on the surface. So the takeaway from this here is that everywhere on the surface of and inside that conductor, the potential is exactly the same. So no matter where you are on that conductor, the potential is exactly equal. So the entire conductor has the same potential. And then we introduce a new word, equipotential. And we're going to be using that word kind of a fair bit in the next couple of lectures. So everywhere on and in the conductor, it's an equipotential because the potential is equal. Still good? So that was a weird shaped conductor. Next, why don't we look at a round conductor, so a spherical conductor, and find the potential inside and on the surface of that one and outside. So let's ask the question, what's the electric potential associated with a spherical conductor in electrostatic equilibrium? The conductor has a total charge Q and it has a radius that we'll call capital R. And then also we'll do a graph of the potential. So we did this sort of question before for the electric field. Now we're going to do it for electric potential. One of the big differences there is direction, of course. The electric field was a vector and this one is a scalar, so it just has a number. So let's do the outside first. So for outside, we mean some value of R bigger than the radius of our conductor. We can draw that if we wish. So here's one value of R, which is greater than the radius of the conductor. Let's write down our relationship between potential and electric field. Delta V is equal to minus E dot ds equals. So our electric field is radial, points radially outwards. And we see that our path is also pointing out. So both of these are radial. So that means we've got minus the electric field dotted with times dr. So because the electric field only has a radial component, only that change in radial distance makes a difference. We remember that electric field is K times Q over R squared when we're outside the conductor. This is one of the integrals I expect you can do. So a power law integral is one of the ones that you might see. We take our constants out front, minus K times Q, outside the integral of 1 over R squared dr. The integral of 1 over R squared is minus 1 over R. And it leaves us with the equation KQ over R. So our electric potential outside of a sphere is equal to K times Q over R. One thing you'll see in textbooks a fair bit, I won't harp on it, since we so often calculate change in potential, that's really important. When you talk about change, it means a change between 2 points. You need a reference point. Our reference point we think about is what is the potential very far away. So if our R was very, very big, so if our R tends out towards infinity, so V as R goes to infinity would be 0. That's what we call a reference point. So whenever you have the situation of a spherical conductor, you're trying to find the potential field, you can use the equation KQ over R because V is equal to 0 all the way out at infinity. And you'll see that in some of the textbook questions if you look through the end of chapter questions to try some different ones, so you'll see that kind of wording there. Okay, so that's outside the conductor. Next we'll talk about on the surface. That'll be our next bit. So on the surface. On the surface means the radius that we're talking about, our distance is equal to the radius of the sphere. So all we have to do here is plug in the radius of the sphere to our equation for the potential. So there's our potential on the surface. The last bit we care about would be inside the conductor. That means the point we care about is less than the value of the radius. So let's say right here. For this one, you got to be careful here. You might start to think about the fact that the electric field is inside is 0, and then that might want to prompt you to say that the potential has to be 0. But you got to remember what we just did on the previous slide, is that the entire conductor, the surface and the inside, all has the same potential. So when we're inside, the potential is exactly the same as what it is on the surface. And then we want to graph that potential. Well, the interesting spot is what happens at the surface. So when we are inside, until we get to the surface, the electric potential is constant. And it has a value of K times Q divided by the radius of the sphere. As soon as we get outside, falls off as 1 over r. And it goes to 0 as r gets really big. So that's what the graph of potential as a function of distance looks like. As a reminder, we might also throw up the graph of electric field as a function of distance. So for our electric field, we can do inside and outside. For our electric field, that was 0 everywhere inside. And then it jumped to a value of kq over r squared at the surface. And then it fell off as 1 over r squared, which is a steeper fall off. So as a comparison, that's how those two graphs are a little bit different. Kind of the same, but not exactly the same. And this one maybe more clearly illustrates the fact that you can have a 0 electric field and a non-zero electric potential. But if your field is ever 0, it means that your potential is always a constant. Questions? Okay, next I'd hoped to bring in the Van de Graaff generator, but the belt is busted on it and it doesn't work, so I'm very sorry, but I'll see if they can get it fixed for me. Who knows, we might get it in before the end of the semester. But anyway, we can do an example which is way more boring than doing a demonstration. So what is the charge? We'd like to find the charge Q on the surface of a 20 centimeter radius. So R is 0.200 meters. Van de Graaff generator, which is charged to 50,000 volts, which is a typical charge on one of these Van de Graaff generators. It's a high voltage. The reason that it doesn't kill you is because it's constant, right? It's change in potential that'll kill you, not potential itself. But don't fool around with potential, it can be really dangerous. So if we wanted to find the charge, we would look at the potential on the surface, which we know V is kq over r. So Q is r times V divided by k. That gives us a charge of 1.11 times 10 to the minus 6 coulombs. So that's a typical amount of charge that would be on the surface of one of those Van de Graaff generators. Okay. Now I'll ask around and see if they can get it fixed for us so I can bring it in class. Or is that boring? Like, would anybody want to see one of the Van de Graaffs in person? Yeah. Okay. Right? Those are the balls you put your hand on, your hair sticks up. Yeah. Okay, I'll see what I can do. Okay, I think we have just enough time to get back to the fourth property of the conductors in electrostatic equilibrium. So I said we were going to do this one when we got to the potential chapter, so here we are. That fourth property stated that a charge density, remember that's sigma, is greater where a curve is steeper. So we're going to consider two spherical conductors, number 1 and number 2. This one has radius that we'll call R1, and it has an amount of charge Q1. This one has radius R2, and it has charge Q2. If we look at our spheres, this one has the steep curve and this one has the shallow curve. So let's see what we can figure out about the charge density. If we think about our two spherical conductors, and they're connected by a thin conducting wire. So everything here is metal. These two things are charged. There's a conducting wire between them. Because it's all metal and it's all touching, everything has the same potential. So we know that the potential of sphere 1 is equal to the potential of sphere 2, because they're all touching and it's all metal, and it's all in electrostatic equilibrium. Potential on the surface of each of these is K times Q1 over R1. That's the potential on the surface of the small one. Potential on the surface of the big one is K times Q2 over R2. We look at this equation, we can divide through by K, so they cancel. Next, we'd like to do something about our Q, and we know our property is about density, so let's tie together charge density and our charge. So our charge density on the first sphere, sigma 1, is Q1 divided by area 1. Area means the area of the sphere, 4 pi r squared. So we can rearrange this equation to see that Q1 is equal to sigma times 4 pi r1 squared. We can do likewise for sphere 2. Sigma 2 is Q2 over A2, and A2 is 4 pi R2 squared. So Q2 is equal to sigma 2, 4 pi R2 squared. Okay, so we've written our charge in terms of our charge densities. So let's fill these in for our charges over here. So sigma 1, 4 pi R1 squared over R1 equals sigma 2, 4 pi R2 squared over R2. A little bit of cancellation going on here. Divide both sides by 4 pi. R1 squared on top divides with R1 on bottom. Likewise for my R2 on this side. So sigma 1 is equal to sigma 2 times R2 divided by R1. So then I divided both sides by R1 to get this expression. If I look at R2 over R1, R2 is bigger than R1. So R2 over R1 is greater than 1. So sigma 1 is greater than sigma 2. Okay, so because R2 is bigger, sigma 1 has to be bigger. What's the meaning of that? So this one has a bigger charge density. To think about the implication of that, we remember about electric field. Electric field is charge density divided by epsilon naught, perpendicular to the surface and out of a positive. So if we have a steep curve, we get a big electric field. Another way to state a steep curve would just be a pointy object. So things that are pointy will tend to have big electric fields. I did want to play a video and bring in the Wimphurst machine. So we don't have enough time, of course, in 2 minutes. So we'll cut there for today, and then we'll be back on Wednesday to finish up this idea. And before you go, please feel free to